speaker is Zilken, and the topic is verifying sampling algorithms by distributional invariants.
Thank you for the introduction. Yes, in my talk we will verify sampling algorithms by using distributional invariants. So probabilistic program verification in general means for a specified precondition to verify a certain postcondition. And we investigate how useful it is to really treat distributions as the main objects of interest. So as a pre and post condition, we really take sets of distributions over the program states. Okay, it turned out our approach works particularly well to verify sampler algorithms, and our running example will be the so-called fast dice roller program. And for the fast dice roller program, we want to verify that when we start the program on any input distribution where n is greater than 0, then on the output, the variable c is uniformly distributed between 0 and n minus 1. So in the end, our goal is to prove this Hoare triple. And yeah, here is the program, the fast dice roller program, introduced by Lombroso in 2013. So it uses a single coin flip inside the loop body, and it computes the uniform distribution for any input n. We can also translate this program into its underlying Markov chain. This is only a part of the Markov chain, namely only the part for the fixed input n equals 3. In general, the Markov chain has an infinite is an infinite object and has an infinite amount of parts for each n as input. And yeah, we want to verify the fast dice roller using distributional invariants. What are those? We define distributional invariant as over-approximations of the reachable distributions. Now, what are the reachable distributions? Here we got inspired by some work in Markov chains. Namely, here we can define the reachable distributions as the unique stream of distributions that are reachable from some initial distribution. For example, if we take our Markov chain for the fast dice roller, the first reachable distribution would be simply the initial state. Then we can apply the transitions of the Markov chain once, and we obtain another reachable distribution. And we can continue this stream forever and obtain a whole set of reachable distributions. Inspired by this notion, we defined reachable distributions directly on program level. So for probabilistic programs, how can we define the reachable distributions here? We take a snapshot of the denotational semantics after each loop iteration. So I hope you're familiar with the denotational semantics. This is basically computing the resulting distribution in a probabilistic program from some initial distribution. And yes, if we have this specific setting which applies to the fast dice roller, where we have a single loop with a loop-free body, we can now take a look at the distribution with which we enter the loop. This would be now, in our example, the Dirac distribution, where v is 1, c is 0, and n is 3. And then we can perform one loop iteration, and we obtain another reachable distribution. So you see this corresponds very well to the Markov chain. We simply collect all the distributions that we reach after a finite amount of loop iterations in one set. And this yields the set of reachable distributions. And now, as I already said in the beginning, distributional invariants are simply over-approximations of these sets. Then there's another notion of inductivity. So our invariants, both for Markov chains and for loops, are called inductive if applying the transitions from the Markov chain for an arbitrary distribution from the invariant yields a distribution in the invariant again. And this is similar on program level. Here I is inductive if executing one guarded loop iteration from a distribution in I yields a distribution in I again. And now one of our contributions was to prove a theorem that really an invariant I is an inductive distributional invariant with respect to a probabilistic loop if and only if it is also an inductive distributional invariant with respect to the underlying Markov chain. So these two notions of distributional invariance really coincide, and we combine the world of Markov chains and loops with this. Okay, back to the fast dice roller. Here we found, a very specific, a concrete invariant to verify the fast dice roller. So this is a set of distributions, and this might look a bit complicated, but these distributions have to fulfill 4 conditions, A to D. And here A, B, and C are basically reachability conditions. So they tell us only the states that you can also see in the Markov chain are reachable. Then we have this condition D, which is really at the heart of the fast dice roller, because this basically expresses that the variable C is at all times uniformly distributed over 0 up to v minus 1. So this is kind of the most important condition, because then on termination we can conclude that v is greater or equal to n, but C is smaller than n, and then we can really have that C is uniformly distributed in the right interval. But how do we do this formally? The last step, we apply a proof rule for probabilistic loops. So if we have found a distributional invariant, we can verify a loop with it by applying one of those rules for loops. So we have 2 rules, one for partial correctness and one for total correctness. So while the rule for partial correctness tells us nothing about termination, with the rule for total correctness requires an additional proof of almost sure termination of the loops, which we also have in our notes, both for the fast dice roller and the fast loaded dice roller. And for the fast dice roller in particular, it is the case that this post condition that we obtain, by the way, the closure of a set of distributions is simply the set itself extended by the limiting distributions. So if we take ascending chains of distributions, we add the limiting distributions to it. And for the fast dice roller and our invariant that we found, it holds that the closure exactly contains all the distributions where C is uniformly distributed between 0 and n minus 1. And by this we obtain our desired Hoare triple, which was our initial goal for the fast dice roller. Okay, this already brings me to the conclusion. So we saw a definition of distributional invariants. They are over-approximations of the reachable distributions, and the 2 notions for Markov chains and for probabilistic loops basically coincide. Then we found out that this framework is particularly well suited to verify sampling algorithms, and as examples in our work we verify the fast dice roller and also the fast loaded dice roller, which is an extended variant which can not only compute uniform distributions but arbitrary discrete distributions. Okay, thank you for your attention.
Thanks, Daniel. Any questions?
How do you generate those distributional invariants? Do you use some like Markov chain-based methods?
No, you have to really find them by hand. So this is not automated yet. Exactly.
Is there some calculus to do that?
Oh, that's a good question. That would be something for our next research, but in general, not, no.
Okay, I think we should move on because we're a bit behind. But thank you very much, Daniel.
Okay.